Hi guys, hi everyone again. Uh, I'm really glad to welcome all of you here, the participants, dear guests, and I'm really glad to introduce this wonderful man here, Dave Abrahams. If you, for some reasons, do not know who he is, he's one of the one of the people who stand behind the C++ in its current state. um, as far as I can tell from my knowledge. But we agree that you will tell about yourself a bit in your talk, so I will not go into details. So, hi Dave.
Hi, Sergey. How are
It's,
you?
it's, I'm fine, thanks. And you?
Wonderful. Excited.
It, Probably it's not 8 p.m. In I can see that there is a sun in your window, so it's
Yeah, it's 9 a.m.
uh,
over
and
here in California.
it's so wonderful time to be alive. It's like we on the opposite sides of the earth, and we can have you on the conference. And I just had a conversation after my talk, people from Novosibirsk, and it's another 4 hours
Hmm.
to the east from St.
Yep.
Petersburg. So I'm still. It's sometimes it's just great to realize that wow, it's all happening kind of magic. Okay, so thank you so much for joining.
Yeah.
I,
So you ready to go?
yeah, поехали.
All right, поехали. All right, I am starting. Hi, so I'm Dave, and I'm proud to be a principal scientist at Adobe's Software Technology Lab. In case you didn't know, Adobe makes software for creative people. We call them creatives. Um, and this image, which we used with permission, was created with Photoshop and Lightroom by Elise Swopes, a photographer and graphic designer in New York City. But I'm here to talk to you about a different creative journey. And to understand that, we'll need to get a little bit of a sense of my background. So, since I'm old, I'm going to take you all the way back to 1998. My first real programming job was for a company called Mark of the Unicorn, making music notation software with a glorious black and white user interface. We were targeting Mac OS, and we had a C compiler. And on that, I built my own object-oriented programming system using the preprocessor. So that was lots of fun. Fast forward to 1991, and my C compiler got upgraded to Semantic Think C, which is like an extension of C with what they called objects. Wasn't exactly the same as C++, um, or even a subset of it, but it looked pretty similar. This is what it looks like. All methods were implicitly virtual. We had regular class inheritance built right into the language, so I could, uh, let go of my preprocessor macros, even though I was sad to see them go. I ported all of my code to use the built-in language features. And by 1995, I was still doing black and white music notation, but I'd at least graduated to a color UI. Also, I had got my hands on something claiming to be a real C++ compiler. And that's when the trouble started. See, this is Mark. Mark is a brilliant guy. He works at Google now. Mark sat in the office next to mine and was always chatting me up about something fascinating. For one notable example, I remember he totally blew my mind describing how a huge collection of documents could be compactly indexed using probabilistic Bloom filters. This was something I'd never heard of before. But the biggest idea he brought to me was in this magazine. Yeah, did you know the PC is dead? Well, Mark had found an article by Alexander Stepanov. and it was about the STL. And honestly, that changed my programming world. The beauty and versatility of this code was amazing to me. And unlike the trivial object oriented application frameworks I'd used, the STL was targeted at real computation, serious algorithms and data structures. And the care with which it was documented made it useful, composable, and confidence inspiring. So I really wanted to start deploying it. But there was a problem. They had left out exception handling. In fact, as this excerpt from Nico Yosudis' book on the standard library says, if anything threw an exception during an STL operation, the behavior was undefined. Now, my program regularly had to recover from out-of-memory conditions. So this was a real problem for me. I couldn't use the STL at all if it was going to crash my program. But because I had had some experience with writing error handling code, I had a decent grasp on what needed to be done to make sense of errors. And I thought the same principles might be applied to the STL. So I looked up Alexander Stepanov's email address and sent him a message explaining what I wanted to do. Alex actually sent me a nice reply saying that it was probably too late to do anything for the first C++ standard because they were already multiple years behind schedule. But just in case, he put me in touch with some people on the committee. And I joined their email lists to discuss the issue. And that's where I virtually met Greg Colvin, the guy in the middle here, who became my steadfast collaborator on exception safety. It was really a huge effort to even convince many committee members that the problem could be solved. But over the course of a year, Greg and I seemed to be making progress. Eventually, though, I got an email out of nowhere from Andy Koenig, who said something to the effect of, well, it's all very well and good to argue your case over email, but you're just wasting your breath unless you show up at a standards committee meeting. So all of that started 7 years of intense involvement with the specification and evolution of the C++ language. I worked on lots of other things, but the most significant was R-value references and move semantics. And then I tried to clean up the damage that caused by adding no except, which I understand is itself still doing some damage today. During this period also, my late friend Beeman Dawes came up with the idea for the Boost C++ library collection as a way to grow the future of the standard library. And I was heavily involved in that project, both as an organizer and as a library author. Out of this effort, I spun off a C++ consulting business and started the first annual C++ conference, which was BoostCon, C++ Now. All of which is to say that the C++ Standards Committee and community had been my training ground for language and library design. And while that was excellent training, I thought of the world in terms of the problems of C++ programmers and the C++ language and ecosystem. But somehow in 2013, I found myself ready to start thinking differently. So I took a job at Apple, working on the secret programming language project that would one day become Swift. And this talk is about which deeply held ideas I confirmed, which I discarded, and what new insights I gained along the way. To be very clear, when I got to Apple, I wasn't thinking about Swift alone. I joined a brilliant group of people with varied backgrounds. And although Chris Latner was in charge, he didn't try to make Swift in his own image. Instead, he basically followed the pattern of design by consensus that I had learned through the committee and through Boost, relying on each of us for our particular talents. And it's my understanding that this is different from how many languages actually develop. Most seem to be the brainchild of a single person. Okay. Now, in one of the earliest design meetings I can remember, there was one person who insisted Swift's strings should be immutable, as in many popular languages, including Java and Python. And this was a belief born of hard experience from dealing with mutable class types in Objective C, the language that Swift was supposed to replace. The problem is that code like this has surprising behavior in many languages, where all compound types have reference semantics. So when you do a copy or an assignment, you're only copying or assigning a pointer, and you end up with shared data, which, if the data can be mutated, is a disaster. See, we were just trying to build a message here, but we ended up changing the intro string. The next time we build a message, it's going to start with hello world and then add world again. We call this effect of changing something you didn't intend spooky action at a distance, with apologies to Einstein. And while it's a source of logic errors on the best days, if intro and message were being handled by separate threads, it's a setup for a race condition. So if you make strings immutable, you may have to change the code a bit. Now reassigning into message, but then when you get to the last line, a new buffer is created by concat, and nothing unexpected happens. Intro is still left where it was. Now, I had come to this project with just one preconceived notion. Swift was going to embrace value semantics for reasons of both correctness and efficiency. At the time, C++ was one of a very few languages that took value semantics seriously. And this was the one thing I was sure I wanted to carry over and amplify in Swift. The basic idea is that mutation isn't the problem. It's mutation of shared state. As it turns out, I didn't really appreciate what it meant at the time, but in many ways, my journey with Swift has been about deepening my understanding of value semantics. And I hope to give you a better sense of that today. Actually, I was hoping to talk about a lot more than that today, but turns out that I learned a lot, so much about that. It's going to take probably the whole talk just to talk about some aspects of value semantics. Now, with the value semantics perspective, a number of problems with the immutable string arrangement were immediately apparent to me. So, first of all, if you actually do have to create a new string buffer for every mutation step, that's really expensive. So if you're building up a string like we did with message, but there are many steps, that's an order n squared operation. So what people normally do in many languages is they make a string builder class. And this is basically a manager for a string buffer. And so it can do mutations. You can do mutations through the string builder, and then it will hand off that string buffer wrapped up in a nice immutable string to you when you're done. Okay, but that's really not great for the complexity of the API, because the string builder, at some point, you actually find yourself, when you're using string builder, needing to read the string. And so you end up republishing all of the APIs that are on the string itself for reading it. All of those immutable APIs end up getting republished on string builder. So that's not great. And it's one more type for the user to learn. Now, I had been given responsibility for Swift standard library, and I really felt strongly that strings should be mutable, but independent values. So I expressed my position the way I had learned things were done in the C++ committee. Over my dead body will Swift have a string builder. Now, that raised a few eyebrows, and I learned that I probably shouldn't use that expression again in a professional setting. But more importantly, this was the first example I can remember of Swift actually saying no to something that would add more complexity than it was worth. And this was a strategy out of which we'd get a lot of mileage, as I hope we'll see. Now, actually, here's another example. In the early days, the compiler was barely usable. It was full of bugs and limitations. And it was really hard for me as the standard library guy to make progress, especially because I wanted to use generics everywhere. Eventually, it became clear that I was going to have to deliver something, so I turned my attention to Swift's array type. Now, the language developers had hacked together something that was sufficient for testing the compiler, but it wasn't really robust, or even really designed. Worse yet, as far as I was concerned, it had reference semantics. The array's buffer was accessed through an object reference. And in Swift, that's a primitive type that's something like a shared pointer to void. I had to fix that. And at that point, I ran up against a problem I didn't know how to solve. See, Swift had no copy constructors or assignment operators. Now, since array used dynamically allocated memory, it was really hard to imagine a way to avoid sharing. As soon as you copy, well, the built-in copy would just copy the reference. It would increment the reference count, but that's it. So, as I said, the language was far from complete. The core language implementers had an enormous backlog of things to do, so I didn't like to bother them, but this really seemed critical to me. So I got a few minutes of Doug Greger's time, and I explained that I might need him to add user-defined copy and assignment operators. And his response surprised me a little. See, this was essentially Doug's over my dead body declaration. I hadn't considered at the time all of the complexity that copy and move constructors, copy and move assignment operators, and destructors added to programming in C++. To me, they were just how it's done, but he had a point. That's a lot of complexity for every type to consider. What am I going to do? I asked. He basically shrugged as though a reference semantic array wasn't the end of the world. Of course, I didn't agree with that, but then he said, just use copy on write. I wasn't actually sure that he was serious. I must have hesitated a moment too long because then he told me to get lost. Now, I had some reservations about this copy on write approach. The first thing I remembered was that GCC's string implementation used to use copy on write, but it was taken out for C++ 11. Now, I didn't know the details, but the reputation was that copy on write had been disastrous for multi-threading. And this is one of those lessons I internalized from my time with C++, and I just assumed that it would present the same problem for Swift. It turns out, though, that the real problem for C++ with copy on write comes from the fact that C++ containers expose unsafe pointers and references to their internals. You can't even read an element without touching an unsafe reference, which could then be persisted and for which C++ makes stability guarantees. Alf P. Steinbach has this wonderful gist that explains the issues in gory detail. But anyway, since Swift collections don't expose unsafe references, that wasn't going to be a problem for us. This was an area where Swift's policy of safety by default actually opened up some new design avenues. So a few interesting things fall out of saying no to the rule of five. So first, all variable sized values in Swifts had to use copy on write. There's just no way to deal with dynamic memory allocation and get value semantics without doing it, right? So you might see that as a downside, but it's got a few interesting upsides. So first of all, copy and assignment never have to allocate memory. It's always O1 to copy and assign, right? Because you're only copying the fixed size of the base object, not whatever it points at. Copy and assignment can never fail. Those are the built-in operations. Just copy the bits and increment the references where needed. Also, reference counting being so fundamental, it's important enough to optimize. And so the optimizer was taught to actually get rid of redundant reference counting. A lot of times, what will end up happening is something that looks like it should be a copy with reference counts just ends up being effectively a move. It doesn't bump any reference counts. Another really interesting thing was that we could add uniqueness check hoisting. Right? So part of the way a copy on write type works is when you're going to do a mutation, first you check to see whether you have a unique reference. If you have a unique reference, then you can take the fast path and mutate the thing in place. Otherwise, you need to build a new value, right? A new result value. And so if you have a series of mutations, that slow path that builds the new value is only needed for the first one. You know after that first mutation that the thing has now got a unique reference. And the optimizer can strip out all of those other slow paths. And maybe most importantly, it's the effect that it has on how we program. It's that we can and we do fearlessly pass arrays, strings, and dictionaries by value. And realizing that leads to this observation of Chris Latner's, which I think is kind of brilliant. He said, yeah, C++ has value semantics, but nobody uses it. Now, that's a bit of an exaggeration, and you have to view things a particular way in order for it to be true. But what Chris meant was that C++, because C++ eagerly copies the element data of containers, nobody really wants to pass them by value. It's too expensive. So let's talk for a minute about parameter passing. As a result, we don't always say in C++ what we really mean. For example, this function, it sums the elements of X, and then it passes each one to a dump callback. Well, it doesn't necessarily do it in that order, but you can't actually tell from the documentation. Doesn't matter, right? So you notice that X is passed by copy. And this function's body owns its copy of X. And even if we use a horrible, evil dump function like this that modifies the thing that we're passing in, the author of sum and dump and the optimizer both know that nothing can modify the X that they're holding inside of body of sum and dump. Right? This is exactly the semantics we want the function to have. But nobody writes this. because nobody wants to pay for copying X. So this is what we read instead. But this change introduced an error. Can you spot it? I'll give you a few seconds. See, the documentation now lies. It used to return the sum of elements in X, and now it only does that if the dump function isn't also mutating X. Right? We've got this. We're not really saying what we mean here. We're passing the parameter, what I call facetiously or disingenuously, right? To C++, pass by const reference really means I'm holding a pointer to it and somebody else might be accessing it. So this documentation now lies. And I'm going to claim that we commonly make similar assumptions about things passed by mutable reference. We code in C++ as though when we've been passed a thing by mutable reference, it's not going to be modified without being mentioned in the code. So on the left, we're just passing y by reference, but on the right, we're doing what's known as a functional update, passing y by value and assigning back into it. And we'll commonly assume when we write the body of this pass by reference function, the call to foo isn't going to modify y, even though that's really only guaranteed on the right-hand side. So in Swift, when we mutate something, we pass it in out. And that really does mean to do a functional update. Well, I lied a little bit. It's actually a mutable borrow if you're familiar with Rust. You won't pay for a copy and reassignment to y, but there's no observable semantic difference. Either way you look at it, the body of frob has exclusive access to y, and that's enforced by and known to the compiler. Okay, this went a lot faster than I thought, and I'm going to close now with what I'm calling Dave's last theorem, with apologies to Fermat, because there's a simple and beautiful proof of this, but there's no room in the talk for it, or at least not in my preparation time. So Swift's model of parameter passing, Swift doesn't support move-only types, non-copyable types today, but this model can be extended to allow non-copyable types to be efficiently passed by value. It will just look like pass by value in the code, or by move with minimal complexity. Now, pass by value of a non-copyable type, Swift can't Swift makes the const ref passing version of parameter passing equivalent to pass by value. Right? So that's why it can look just like pass by value. We don't need a fancy reference. And this model could be applied to a future version of C++. So when we're thinking about the future evolution of C++, one thing we could really do is find a way to say no to complexity in parameter passing. Thanks very much. That concludes the presentation.
Dave?
Yeah.
And
Sergey.
we already have questions, actually. It's more or less general, not just about the talk.
Okay.
Just general about evolving new language. Like, how do you battle test a new language? Well, you need on one hand to evolve it and quickly involve it, and on the other hand, collect the feedback.
Yeah. I actually had notes about that for this course. Open source works. It works really, really well. I don't think I want to ever use a language that isn't open source. So you get the community involved. Um, uh, we were very lucky with Swift because at Apple we had a captive user base. A lot of people were going to start using it, and that's one of the reasons I got involved with that project. Getting involved with a language project is risky because languages come along every week and they just die in obscurity, right? Because nobody's using them. So we had a very special opportunity with Swift to get a whole lot of users very quickly. And what you would do with a different scenario, I don't know. Um, yeah, I don't have advice for somebody that doesn't have a way to get a huge amount of users.
So just convince Apple to use your new language, right?
There you go. Convince Apple to give up on Swift and use your new language, because they haven't invested enough money in Swift.
That's brutal. So some of the decisions seems to have overhead. That's the next question. How much overhead was acceptable for you? How did you measure that?
Yeah, well, so this is a really interesting point, because one of Swift's design criteria was, like, one of its fundamental goals was to be able to have a stable ABI that you would also let you extend classes and structs, add new fields, change the layout of data types. And that has some inherent costs. So that's built into the model. But the strange thing is that the only place that model actually gets used is at Apple. It gets used for the boundary between the operating system and applications, so that the operating system can be upgraded and applications will continue to work, and vice versa. Okay, so what that means is that essentially, in principle, everything else can be inlined visibly, right? And in principle, you could do any optimization that's possible knowing the whole program. Of course, that never works out in practice, right? The optimizer always falls down at some point. So I guess we did the best that we could, given the absolute minimal constraint that the basic model was going to have this essentially type erasure boundary at module boundaries. But we were very aggressive about erasing it where possible. It's a different set of efficiency trade-offs. I can tell you that there are people, and I have not verified their claims, there are people who use Swift who report having done comparisons with C++, and their programs run faster in Swift. Now, I'm not saying that's going to be universal, but there are some reasons to believe it might be true. All the extra information that the Swift compiler has about what data is accessible allows it to make optimizations that a C++ compiler can't. Right? Every time you get something by reference or by const reference in C++, the compiler has to assume that it's being aliased by things all over the place.
Yeah, sure. So, and logically, we came across the last question that we have. Probably we'll discuss here, and then we probably will join the discussion at Zoom. Yeah. So, do you see Swift as a replacement for C++ and general app development, like beyond Apple platforms?
I think it could be. I think so. There are many. There are many directions being considered by the community right now for what to do about the future of C++. Because I think there's general agreement, maybe not universal agreement, but there's general agreement among a lot of people that C++ has sort of reached a limit of its ability to grow without just becoming completely overwhelming. And in a lot of ways, I think it already is. I left the community in 2013 to go work on Swift. I've come back. I was a world-class C++ programmer when I left. Now, I think I barely know the language. So much has changed, right? And there's so much more of it. It's just a lot more of it. So I think there's a general consensus that something needs to be done, whether it's some kind of next version of C++ or moving to another language. What I think is really interesting, though, is that for a language with if you look at a lot of the potential replacements for C++ that are out there in the world, I guess the two obvious ones that I can think of are Rust and Swift. But if you look at both of those, either of them could be eventually a suitable replacement. But the problem that hasn't been solved for either of them is sort of a general problem of how do you make a modern, sound, and safe language interoperate with C++ reasonably. And I think the problems needed to do that are pretty much the same for both of those two languages, even though Rust and Swift have a very different implementation model. And so I think that's really the more interesting question. It's less, can Swift replace C++? Can Rust replace C++? Can C++ develop a new version? It's really, can we figure out how to make C++ as it is today interoperate with something that's cleaner and more modern, whatever that turns out to be.
Thank you. It's really a lot to think about. And thank you again for joining. I remind all our listeners that we will continue in Zoom. So if you want to ask a question, just join the discussion.
Okay, wonderful. Thank you for having me.
Thank you.
Bye, everybody. I'll see you in Zoom.
Yeah, see you in Zoom.